Well, yes in the back? Well, I'll talk about something that's not that important while we work out. You can decide whether it's going to actually you can hear me or not. So a number of people have asked me about midterms, which is coming up next week, I guess, a week from Friday, I believe. So check that. And the questions always revolve around how should I study for this exam. So the first thing is the lectures, at least the material you'll be tested on, is independent from the laboratories. Okay, so we'll not be testing you on material you learned in the laboratory, although there's hopefully at least some overlap. That is to say that the material will reinforce each other. But I would concentrate on my lectures. Sorry? Yeah. Let's try this. How about now? Is that better? I can't move here. How about now? I've got this up to maximum, I swear. In the back, is there anything else? This is sounding okay now. All right, so thank you. So hopefully that's resolved. So I would concentrate on the lecture material that I say in my notes. Remember in the very beginning I said, what are you responsible for? Well, anything that I say in lecture and anything that's in my notes is fair game. Remember, I don't quiz from material directly from the book. Right? So you can use that if you want. You can read through the book if you were uncertain of a concept. Maybe it'll be better explained there. But lecture material and notes. Now, you need to use common sense because in anything, you can't, well, maybe you can know everything, but you need to concentrate on the things that you consider the most important. I'll tell you what I consider to be the most important. My feeling is that it's the concepts. Not so too noisy, too loud. Concepts first, major ideas I presented. That is to say, I gave you an evolutionary explanation for various biological phenomena. You should understand the phenomena that we're trying to explain and the evolutionary explanation, the model. And I tried to, as much as possible, give you concrete examples. Okay, I tried to give you concrete examples. I gave you concrete examples of natural selection in the wild. I gave you examples of artificial selection in the laboratory, just as, to start from. Okay? And then, of course, if you're probably better off getting on top of the studying earlier rather than later. You would not believe how many emails I get at 2 in the morning the night before the lecture, which of course I can't. I'm sleeping then, as it turns out. So I don't really have time to answer these. But about last-minute questions about this or that. I'm happy to answer the questions, but they have to be in a timely manner. The best thing you can do is come to office hours or come to my office. Remember I told you that, especially in the afternoon, I'm usually around 4161 BLSB, 4th floor of this building. And the best thing you can do is if you're in the area, that is to say, I know some people can't make my office hours, which are directly after the lecture. But if you're in the area, well, maybe I'm around. Stop by. If I'm there, I'll take the time out to talk to you. All right? Drop whatever I'm doing, and I'll answer your questions. Okay? So that's what I would do for studying. Are there any other questions about the midterm or what we're going to be doing there? Yes? Well, if they're in the notes or I say them, then of course technically you're responsible for them. But once again, you have to give yourself some priorities. Like what are the things you want to study for first, and then once you know all the concepts, then you can fill in all the details, right? That's how I would study. Go from the top down. In general, I'm not going to tell you what's on the exam. That's silly. But in general, what I consider the most important are the concepts, and then I'd like you to be able to give examples supporting it. I try to design the exam so that if somebody really studied hard, but they really didn't quite get it, that at least they get some points. That there's material that if you did just do rote memorization, you do pretty well. But to get an A, I'd really like you should be able to not only know the concepts, but give supporting examples. And that's my real goal. And so I try to design the test to distinguish or discriminate between those people who really do know everything and those people who work hard but didn't quite get it all, right? So and of course then there's those people who didn't take the time to really work hard and study material. They're not going to do as well probably. Okay, one more question. Yes. It's multiple choice, and this class is the largest I think it's ever been. It's 850 students, and as much as I really do believe short answer and essay questions are probably the best in terms of giving you the best chance to demonstrate your knowledge, and also they're the easiest, frankly, the easiest to give good questions for. Like you really can discriminate people like I want to, but you can't do it. It's just not practically possible. All right, one more question. Yeah. That is a good question. I do not know. So you remember this course is so big it has a course organizer, Mike Moser, right? And so that would be a question I can find the answer to in the next lecture, but also Mike Moser will be able to answer that. Is there a TA here who knows the GSI here who knows the answer? All right, if they're here, then there's clues on design about this one. Sorry. Okay, I want to. We have 4 more lectures, yes, and I want to give you some sort of overview of where we're going. Okay, so I'm going to make a little evolutionary tree. All right, there's our evolutionary tree. Obviously, I just made it up. Okay, but this is idea. There's this metaphor that Darwin also used, which is a sort of tree of life. It's to say that all species on Earth are related one to the other, and these relationships can be depicted, and usually when they're depicted, they're a tree-like diagram like this. And it's called the tree because it looks like a tree in terms of branching pattern. There's also mathematical topic about trees in graph theory. But the idea is that the tips of the twigs of this tree, the tips actually make it to the top. Those are the species that we have alive today. But there's a long history of, on Earth's history, this tree of life goes back billions of years, and to the point where you have a common ancestor for all living species on Earth. Okay, this would be the most recent common ancestor of all living species. And we think that there is a common ancestor because all living species share characteristics, and really basic characteristics. I gave you some, such as sharing a universal genetic code, very similar genetic code. They use the same 20 amino acids. All species use a very similar mechanism for making proteins. The machinery is very similar. Okay? So these characteristics make us think that all organisms living today share a common ancestor. Now, of course, the origin of life would have been sometime before that. There's probably lineages that are no longer alive today, which would have been fascinating to study where there were different experiments. Who knows, right? We can't really know that. But we can know that there was a common ancestor for all species, and it lived billions of years ago. Today, the number of species living today is in the millions. It's hard to know exactly how many species there are, 3 to 30 million. So that's a pretty big range. But that the diversity we see today is very great, but it all came from one species that lived in the very distant past. So to get from one species to millions of species, you have to have these speciation events. That is to say, you have to have many events where you had one lineage split into 2 lineages. Okay? That is called speciation, and that is the topic of today's lecture. So we're going to be concentrating on these points here, where one species where you get 2 species from one species. That's speciation. Now, of course, you might imagine the details for any one of these millions of speciation events that occurred in the past might be different, every one from the other. So what we're going to be trying to do is talk about general concepts, general rules of thumb that could actually generate species. Right? So we're going to talk about models again, right? Models about describing different processes that can cause species to form. I should just mention here too, just to link this to last lecture, we think about every one of these lineages as being a species. And from our point of view, we're going to be using the biological species concept, BSC, biological species concept. which is to say that if we were to take an individual from this lineage, this species, and try to breed it with individuals from this species, that would not work. This is to say that these individuals from these two lineages, these two species don't freely interbreed. But if you were to take two individuals from any one of these lineages, they do freely interbreed under natural conditions. That's what we're talking about. That's a species. So last lecture, we talked about what species are. This lecture, we're going to talk about how speciation occurs. The next lecture, we're going to be talking about how to actually infer the branching diagram. How do we come up with trees that we think are best estimates of what really happened, what the real tree of life is. And in the very last lecture, I have a guest lecturer who's going to talk about one twig, the twig of life, the twig that leads to modern humans. Right? So that's the twig that a lot of us are probably particularly interested in, right? So that's going to be the last lecture. Okay, so speciation. Speciation, well, let's write it there. We have one lineage. This is the speciation event. The question is, what type of processes, what type of events cause reproductive isolation between two populations? So the idea is that we have populations. There's two populations of a species. We have migration or gene flow between the two populations. We spoke about this when we talked about population genetics. Migration is a process that will bring alleles from this population to this one and vice versa. Okay? So the point here is, the important point with migration or gene flow is this. If you have a mutation, I can't make lightning bolts, it turns out. If you have a mutation that hits this population, that lands in an individual in this population, through gene flow, eventually that mutation can get over here. True? You have an individual that happens to have that mutation just migrates over this population, then that mutation can get over this population, and vice versa. So gene flow is a process that reduces the variation between two populations. It makes two populations look more and more the same, genetically. But what happens if we eliminate gene flow? What happens if we eliminate gene flow? Well, then any mutations that occur in this population are going to be limited to this population. There's no way they can get over here. And vice versa. If you have a mutation that occurs here, there's no way for it to get into this population unless you have it independently occur on some individual in this population, which is unlikely. Okay? So when you turn off gene flow, if you can think about there being a knob, population genetics knob where you turn gene flow to 0, as I say, you don't let individuals migrate from one population to another, these two populations over time will become more and more different one from the other. Processes such as mutation, genetic drift, and natural selection can be fixing various alleles differently in both populations. They'll become more and more different over time. Okay? So this initial split, the thought is that there's some sort of mechanism, somehow, in some way, gene flow is turned off. We'll talk about different mechanisms, different types of mechanisms that can cause gene flow to cease. Okay? The first step has to be eliminating or turning off or stopping gene flow between populations. After which you have more and more changes accumulating in the two lineages. And so an important question in speciation is this. Let's say at some later date, so after tens of thousands of years, say, individuals from these two populations or incipient species come back into contact. So all of a sudden you have males from this species have the possibility of mating with females from this population. The question at this time is, does that work? Okay? And it depends. So we will talk about reproductive isolating mechanisms that can arise during this period where they're in isolation and you have changes accumulating independently that can cause these reproductive isolation when these species finally come back into contact, one with the other. So for instance, it's possible, one possibility is that when these individuals come back into contact, that they can freely interbreed. And the two incipient species, if we want to call them that, would merge back into one. This would be an example where we did not have different species being formed. But the other possibility is that the types of incompatibilities that arose during this period when they're isolated one from the other, when gene flow was turned off, were such that they can no longer successfully interbreed. So what types of isolating mechanisms, what types of reproductive isolating mechanisms can evolve? Mechanisms. So there are two major classes of isolating mechanisms that reproductive isolation can evolve. The first is called prezygotic isolation. What is prezygotic isolation? These are isolating mechanisms that prevent a zygote from being formed. Remember, a zygote is a fertilized egg, right? So what types of mechanisms can cause or can prevent fertilization in the first place? Well, there's a lot of them. There's behavioral differences. There are behavioral differences that can arise during this period when the species are in isolation or when gene flow has been turned off. Lots of species have courtship displays, as an example, right? So in cases where you have female choice and the female is choosing the male, she might be choosing males based on some sort of display. And if that display is quite different, she might not even recognize that male as being from the same species or a good mate. Okay? So that would be an example of a behavioral difference that can evolve. I mean, and many species do it. You're probably thinking birds that clearly have songs and dances and behaviors, that courtship behaviors that females might recognize. But flies, for instance, insects also have these types of mating behaviors. And the females just may not recognize a particular behavior as being right, okay, that she recognizes that as being an individual she wants to mate with. And there's a good example. I will be revisiting this one, but I'll be revisiting this example of these Ragelitas flies that live on hawthorn and now apple and cherries and other fruits and spoil them. But Ragelitas, they mate with individuals only that only lay their eggs on a particular kind of fruit. So you have, say, an apple, and you have the female. There she is. Oviposits on the apple, and the male's going to be also laying on that same apple, or mating with the males out here flying around, and they basically hang around the same type of fruit that they hatched off of. So you have females revisiting the same fruit they hatched off of, males also flying around, buzzing around fruits that they hatched off of. And so you have basically this type of behavioral isolation where their behavior is to hang around fruit of a certain species. Okay? But this would be an example of if you have, for instance, divergence in the type of fruit that you oviposit on, you can actually have divergence in this way. You can have what's called temporal isolation. There's lots of species that live cheek to jowl one next to the other, but because they mate at different times, they're reproductively isolated one from the other. So as an example, many flowering plants flower and produce pollen at different times of the year. Right? That would be one way of becoming reproductively isolated. Many marine invertebrates spawn their eggs and sperm into the water column, but because they do that at different times of the year, the eggs and sperm from different species never have the chance to contact each other. Another example of a temporal isolation of different species. And let's talk about another one, mechanical. This is just what you might imagine. It's, many species, the male and female genitalia just will not fit one into the other. called the so-called lock and key mechanism. But it's often the case that many species, the genitalia is the most rapidly evolving part of the anatomy. In flies, for instance, there's cases where the fly adults look identical one to the other as far as almost any expert can tell, and the way they can tell whether you're dealing with a fly from one species to another is they turn them over and look at their genitalia, because the genitalia are so different one species of fly to the next. But it's a case that mechanically, in many species, even if different flies as an example, they just will not work because of the so-called lock and key mechanism. These would be all mechanisms that would prevent species from an egg even being fertilized in the first place. Let's go to post-zygotic isolation next. I think I should probably go to the board. I believe I have, for the display, I believe I have material to show you here. Never really realized how slow this screen is. All right. Okay, so we spoke about pre-zygotic isolating mechanisms. These are mechanisms that we all recognize as preventing the fertilization of an egg in the first place, preventing a zygote being formed in the first place. Here's an example where these pre-zygotic isolating mechanisms failed. Okay? And I think people are always interested or fascinated by these examples because they recognize that somebody made a big mistake at some point, right? I think that's the idea. And here's an example of a liger. We have a male lion mates with a female tiger. This often happens in captivity. Okay? Captive situations, sometimes these animals are not acting quite normally. But here's an example of a liger. In these cases, the ligers are actually tremendously large animals. They're very large, but they're also not very fit. I believe they're actually sterile. Here's an example where that's true as well. Here's a mule. You've probably all heard that mules are from a mating of a donkey and a male donkey with a female horse, in which case they're called a mule. Mules are sterile. And almost all mules are sterile. There's always exceptions to the rule. This is biology, but in almost all cases, with just a few exceptions, mules are sterile. And there's also hinnies. Some people here probably have heard hinnies, but they're just the opposite cross. You take a female donkey and cross them with a male horse. Okay, but you can have this type of mistake made. Once again, mules you kind of recognize as being very hardy animals, but with the one exception being that they're sterile. So they're deliberately made because they're actually pretty hardy animals and useful in many circumstances. There's another case of a mistake, a zebroid. Here we have a female horse mating with a male zebra. Okay, so these are examples, plenty examples if you will, but examples you might have been aware of cases where these pre-zygotic isolating mechanisms failed. It happens in the case of nature that hybrids, these are called hybrids. Hybrids often form in nature as well. Do you have a question? Yeah. Not all. So we'll talk about it. It can be varying degrees. So one possibility. I mean, the interesting thing about these isolating mechanisms is it really depends on how long since the gene flow, how long they've been diverging. These populations have been diverging separately, right? As time goes on, more and more genetic differences are accumulating. Okay? And the idea is that at some point these genetic differences become so great that either the species have diverged so much that you just never get mating occurring in the first place, that the species just don't, it's not possible, or they don't recognize each other as being possible mates, or if they do form, or if they do try to form offspring, that the offspring that formed are well, there's varying degrees. They could be not as fit, as I say, they can still produce offspring, but you have to think that two different species, let's imagine two different populations, both diverging under the combined effects of mutation, natural selection, genetic drift, right? In isolation, one from another. Well, natural selection can operate differently, will operate differently in these two different populations. Natural selection will hone the two different populations to be well adapted to their different environments. Right? So you might imagine that if you have two different populations well adapted to their own environments, when you make hybrids, they're going to be poorly adapted to either of them. This is called ecological isolation. I'm not going to be talking about it really, but it's possible that the hybrids that are formed, even though they can form offspring themselves, are themselves not particularly well adapted to any environment. That would be an example of kind of the most mild form of reproductive isolation. And then the most extreme would be the zygote is formed but it fails to develop. That is to say that the lethal types of incompatibilities have arisen, and everything in between. Right? So the point is that this is a general model, and what you actually observe in any one hybrid cross, that is to say, any one instance where you form hybrids can be anywhere along the spectrum. Okay? All right, so post-zygotic isolation, what types of mechanisms, what can happen here? Well, the most extreme, like I just referred to, is the zygote doesn't develop properly. Okay? It could be a lethal incompatibility. Or you could have reduced fitness, for the reasons I just described. Maybe the hybrids are not well adapted to any particular environment, or they could be sterile. As I say, even though they're alive and perhaps even well, they can't form children themselves. They're reproductive dead ends, so to speak. And as an example, the donkey-horse cross. Let's see, well, the donkey has 62 chromosomes, whereas the horse has 64 chromosomes. So the mule that forms, it's possible that it cannot actually form good gametes because of problems during meiosis. So it's not to say that the mule is necessarily missing any genes, but that you can have problems with good sperm and egg being formed. So anyways, this is just, actually I should probably give you the best model that's out there. So there is actually a model describing how these genetic incompatibilities arise and can cause hybrid sterility or death. Okay? I'm going to give that to you right now. Brace yourself. I think the best way of introducing this model is to give you a wrong model first. Right? So whatever I say right now, don't remember this. Right? This is just for pedagogical purposes. But I think this is the best way of understanding this model. So we're going to imagine we have two species, this species and that species, and there's their common ancestor. Okay? And this is the wrong model is a one locus model, one gene, one locus. We're going to imagine that the ancestral species was little a at this locus.